heading perfectly elastic collision in one dimension. Okay, it is very important. Perfectly elastic collision in one dimension. Perfectly elastic collision in one dimension. Okay, laboratory frame. A laboratory frame. Okay, let M1 and M2 be the masses of two particles. Be the masses of two particles. Masses of two particles. U1 and U1 vector and U2 vector and V1 vector comma V2 vector, their respective velocities. Their respective velocities before and after an elastic. Before and after an elastic one-dimensional collision. An elastic one-dimensional collision. Okay, one-dimensional collision is that a head-on collision along the line joining their centers. Then an elastic one-dimensional collision is that a head-on collision along the line joining their centers. Then M1 U1 vector plus M2 U2 vector equal to M1 V1 vector plus M2 V2 vector. Okay, this is the equation number first. Okay, and according to the law of conservation of energy, according to the law of conservation of energy. Okay, M1 U1 square plus M2 U2 square equal to M1 V1 square plus M2 V2 square. This is equation number second. According to the law of conservation of energy. Okay, rewriting equation first and second, and taking magnitude only we have, and taking magnitudes we have, magnitudes only we have M1 U1 minus V1 equal to M2 V2 minus U2. Okay, and M1 U1 square minus V1 square equal to M2 V2 square minus U2 square. This is the equation number. This is equation number 2. This is equation number 3, and this is equation number 4. Okay, and dividing 4 by 3 we have E1 plus V1 equal to V2 plus U2 or U1 minus U2 equal to minus V1 minus V2. Okay. This shows that in the elastic one-dimensional collision, this shows that in an elastic one-dimensional collision, one-dimensional collision, the relative velocity with which the two particles approach each other before collision is equal to the down sound down equal to the relative velocity with which they recede away from each other after collision. Okay. This shows that in an elastic one-dimensional collision, the relative velocity with which the two particles approach each other before collision is equal to the relative velocity with which they recede away from each other after collision. Okay, after collision. Okay, velocity after collision. Velocity after collision. Okay. From equation 5 we have equation 5 this is 3 and this is 3, this is 4 and this is 5. Okay. From equation 5 we have V1 equal to V2 plus U2 minus U1. Okay. And V2 equal to V1 plus U1 minus U2. Okay. Substituting the value number V2 in third, we have M1 U1 minus V1 equal to M2 V1 plus U1 minus U2 minus U2. Okay. By the equation third. By equation number third. Okay. By equation number third. And V1 in bracket M1 plus m2 equal to m1 minus m2 u1 plus 2m2 u2, okay? Or v1 equal to m1 minus m2 upon m1 plus m2 u1 plus 2m2 upon m1 plus m2 u2. This is the equation number 6. Similarly, v2 equal to m2 minus m1 whole upon m1 plus m2 u2 plus 2m1 upon m1 plus m2 u1. This is the equation number 7. Okay? This is the equation number 7. Okay? This is the equation number 7. Okay? 1 minute. This is the equation number 7. Okay? Special cases. Okay? Case first. Okay? One of the colliding particles is initially at rest. Is initially at rest. Let m2 be initially at rest, then u2 equal to 0. Hence v1 equal to m1 minus m2 upon m1 plus m2 u1 and v2 equal to 2m1 upon m1 plus m2. This is the equation number m2 u1. This is the equation number 8. Okay? Case second. Okay? The particles have the same mass. The particles have the same mass. The particles have the same mass. In such a case, m1 equal to m2. m1 equal to m2. Hence, in one-dimensional elastic collision, as in one-dimensional elastic collision of two particles, two particles of equal mass, the particles simply interchange their velocities after collision. Okay? Second case, the particles have the same mass, that means m1 equal to m2. Hence, in one-dimensional elastic collision, if two particles of equal mass, the particles simply interchange their velocities after collision. Okay, if M2 is also initially at rest, if M2 is also M2 is also initially rest, then U2 equal to 0 and V1 equal to 0, and before as before V2 equal to U1. This is the equation V8A. This is equation V8A. Hence the first particle of mass M1, the first particle of mass M1 comes to rest after collision, come to rest after collision, and the second particles of mass M2 acquires the initial velocities of the first, okay. If M2 is also initially at rest, then U2 equal to 0 and V1 equal to 0, because in our second case the masses are also equal to, that means M1 and M2, V1 equal to U2, and substituting 7 V2 equal to U1, okay. Hence, in one-dimensional elastic collision of two particles of equal mass, the particles simply interchange their velocities after collision, okay. And if M2 is also initially at rest, then U2 equal to 0 and V1 equal to 0, and as before V2 equal to U1, hence the first particle of mass M1 comes to the rest after collision, and the second particles of mass M2 acquires the initial velocity of the first, okay. Hence the first particles of mass M1 comes to the rest after collision. M1 comes to the rest after collision, and the second particles of mass M2 acquires the initial velocity of the first. Third case third, okay. Third case. 1 minute. Case third, okay. The particles at rest is very massive. The particle at rest is very massive, okay. Massive. The particle at rest is very massive. If M2 is very heavy as compared to M1, if M2 is very heavy as compared to M1, and U2 equal to 0, then, okay. Then M1 equal to 0, comma, M1 minus M2 equal to minus M2, and M1 plus M2 equal to M2, so V1 equal to minus U1 and V2 equal to 0. This shows that when a very light particles collide against a very massive particles at rest. The heavy particles continues to remain at rest and the velocity of the light particles is reversed. Okay? This shows that when a very light particles when a very light particles collides against a very massive against a very massive particles at rest. Particle at rest, the heavy particles continues. The heavy particles continues. The heavy particle continues to remain at rest, and the velocity of the light particle is reversed. Light particles is reversed. Okay? Is reversed. This shows that when a very light particles collide against a very massive particle at rest, the heavy particles continue to remain at rest and the velocity of the light particles is reversed. Okay? A familiar example of this is dropping of a steel ball. Okay? Dropping of steel ball. Okay? Steel ball. Dropping of a steel ball on an equally hard horizontal surface on the ground. Okay? Horizontally surface on the ground. This is in fact a collision between the light ball and the massive ground at rest. The velocity of the ball is reversed on impact. This is judged from the fact that the ball rises to the same height from which it was dropped. Okay? Case fourth case. Okay? Particle at rest is very light. Particle at rest is very light. If the particle at rest is very light, then m2 equal to 0 and m1 minus m2 equal to m1 and m1 plus m2 equal to m1. Okay? Substituting in relation eight, we have v1 equal to e1 and v2 equal to 2e1. Okay? This shows that the velocity of the heavy particles remains almost heavy particles heavy particles remains almost the same after the same after collision the same after collision and the light particles and the light particles acquires nearly twice the velocity of the heavy particles okay. This shows that the velocity of the heavy particles remains almost at the same after collision and the light particles acquires nearly twice the velocity of the heavy particles. Okay. Case B point. Center of mass frame. Center of mass frame. Okay. Center of mass frame. When no external force is acting, the velocity of center of mass is given by when no external force is acting, the velocity of center of mass is given by VCM. Center of mass. Velocity of center of mass is given by m1 u1 vector plus m2 u2 vector upon m1 plus m2. Okay. As the collision is one-dimensional, therefore taking magnitude only VCM equal to m1 u1 plus m2 u2 upon m1 plus m2. Okay. Locality of the particles of mass m1 before collision related to center of mass frame according to Galilean transformation is given by according to Galilean transformation is given by E1 vector equal to E1 vector minus V center of mass vector velocity of center of mass vector equal to E1 minus M1 E1 vector plus M2 E2 vector upon M1 plus M2. Okay. Upon M1 plus M2. Okay. Equal to M1 E1 vector plus M2 E2 vector minus M1 E1 vector minus M2 E2 vector whole upon M1 plus M2 equal to M2 E1 vector minus E2 vector whole upon M1 plus M2 taking magnitude only only E1 dash equal to M2 E1 minus E2 upon M1 plus M2. Okay. Velocity. Okay. 1 minute. Velocity of the particle of mass m2 before collision. Velocity of the particle particle, velocity of the particle of mass m2 before collision, before collision relative to center of mass frame according to Galilean transformation is given by u2 vector equal to u2 vector dash equal to u2 vector minus b center of mass vector equal to u2 vector minus m1 u1 vector plus m2 u2 vector upon m1 plus m2, okay, equal to m1 u2 vector plus m2 u2 vector minus m1 u1 vector minus m2 u2 vector whole upon m1 plus m2, okay, equal to m1 u2 vector minus u1 vector whole upon m1 plus m2 okay, whole upon m1 plus m2 because m2 u2 minus m2 into each cancel out. So m1 is common in bracket u2 minus u1 upon m1 plus m2. Okay, taking magnitude only. Taking magnitude only. Taking magnitude only. u2 dash equal to m1 u2 minus u1 upon m1 plus m2. Okay, velocity after collision. 1 minute. Velocity after collision. Velocity after collision. Okay, velocity after collision. The velocity of the particles of mass m1, the velocity of the particles of mass m1 after collision relative to center of mass frame according to Galilean transformation is given by v1 dash vector equal to v1 vector minus v center of mass vector. Okay, then v1 dash equal to v1 minus v center of mass equal to m1 minus m2 u1 plus 2m2 u2 whole upon m1 plus m2 minus m1 u1 plus m2 u2 whole upon m1 plus m2 equal to m1 u1 minus m2 u2 plus 2m2 u2 minus m1 u1 minus m2 u2 whole upon m1 plus m2 equal to minus m2 u1 minus u2 whole upon m1 plus m2. This is the equation number 10. Okay. The velocity of the particle of mass m2. The velocity of the particle of mass m2 after collision in the center of mass frame according to Galilean transformation is given by v2 vector dash equal to v2 minus vcm. Okay, taking magnitude only, v2 dash vector equal to v2 minus vcm equal to m2 minus m1 u2 plus 2 m1 u1 whole upon m1 u1 plus m2 u2 whole upon m1 plus m2 equal to m2 u2 minus m1 u2 plus 2 m1 u1 minus m1 u1 minus m2 u2 whole upon m1 plus m2 equal to minus m1 u2 minus u1 whole upon m1 plus m2. This is the equation number 11. This is the equation number 11. Okay. The center of mass is at rest. The center of mass is at rest. Is at rest before and after collision. Before and after collision. Before and after collision. Before and after collision. Okay. Before and after collision. Relative the center of mass. Relative the center of mass. Center of mass. Reference frame. Reference frame. Okay. Reference frame. The center of mass is at rest before and after collision. The center of mass is at rest before and after collision relative to center of mass reference frame. Okay. Thank you. This heading is left and next heading is perfectly inelastic collision in one dimension. Okay. Thank you. Next heading.